All right, so last class we did not finish 1.3. Just there was one more thing I wanted to discuss. So it's this example here, 1.3.17. Oh, by the way, I've already met with some of you for that bonus 5 points, that sign-in sheet. People had come into my office. I forgot to bring it today for people to sign up. So if you want to sign up today, you can follow me to my office afterward. If not, I'll bring it next time. We'll pass it around again, okay? All right, so here we go. This is kind of an unusual problem. I've been known to give a problem like this on the test. It says for you to sketch an example of a function with the following properties. So you need to draw a picture for me that has these 7 properties listed. Now, the first word that we should be aware of here is that whatever we draw needs to be a function, which means that it needs to pass the vertical line test. So after we're done drawing, better pass that test. All right, so let's start out here. The first condition is that the limit as x approaches -2 of the function must be equal to 3. So what does that mean? Okay. Is what? You're coming in from the left side. Okay, so as we come in from the left side of what though? The x value? Okay. Our function should be approaching 3 on the y value. But as our x is approaching what though? -2, right? -2. So if I go to -2 on the x, my function should be approaching 3. From which side though? Why left? Okay, so I intentionally put this here to trick you. The thing that tells you left or right is a plus or minus put in the top right corner of the number right there, right? If I put a plus there, then that would mean approach from the right. If I put a minus there, it means approach from the left. If I don't put anything there, what does it mean? Both sides. So we are approaching the x value of -2 from both sides. The y coordinate should be approaching 3. So that means when I draw my function, if I am approaching -2 from both sides, my function should be approaching 3. So I'm going to go ahead and put that here. Would you agree? Just tell me if you agree with this or not. Would that satisfy the condition? As my x value approaches 2, from the left, my function is approaching 3, and from the right, my function is approaching 3. Does that satisfy number 1? It's not a function? If I do the vertical line test, I just can't hit it more than one time, right? So right now, even though I drew a vertical line here, I wouldn't hit anything, that would still be okay. It would still be a function. So we're okay then? Okay, so first condition is met. Agreed? Now I left an open circle there. I could have filled in the circle, couldn't I have? Like I could have, but then look at number 2. What is number 2 saying? F of -2 is 0. So at -2, the function's value needs to be 0. So right there, a dot right there, yes? So when I put this dot here, that would have eliminated the possibility of me putting a dot here. So I left it open because the limit didn't tell me anything about what's happening at -2, right? It only tells me about what's happening from the left and the right. So I left it open, and good thing I did because part 2 says at -2 I have to be 0. Any questions on that? Sure? Okay, what about the third condition? Well, sorry, oops. 1, 2, 2. So obviously I messed up there. But what about this condition right here? What is this telling me? And let's start calling names today. James. Where's James? There you are. I was like, where'd he go? Okay.
It's approaching -1 as it approaches 1.
So the function's value is approaching -1 as x approaches what?
1 from the left.
1 from the left. So as we approach 1 from the left-hand side, can you all see that little negative sign? As we approach 1 from the left, our function should be approaching -1. So I go to -1 here, that's where I'm approaching, as x approaches 1 from the left. So from this side, my function should be approaching this value. So I'm going to put an open circle, and how about I just put a little tail like that? Would that satisfy that condition? So we approach 1 from the left, our function is approaching -1. I'm going to have to put all these things together. I'm just using the information to draw like little snippets of what my function's doing. Okay, what about Edward? Cool, we just met. How you doing? How about this next condition? We've done this one. So what is this saying?
As the function is approaching 1 from the right,
Uh-huh.
fx
Is approaching 2, right? Approaching 2. So we just approached 1 from the left, didn't we, to do this one? Now we need to approach 1 from the right, but now my function should be heading up towards 2 instead. So right above 1, I'm going to go up here, I'm going to draw a circle like that, and I'm going to do a little tail out the side like that. Yes?
How do you know whether you want to put the tail up or down?
That's up to you. The question was, do I put this little tail up or down? It doesn't matter so long as it satisfies the condition. Like that would satisfy it also. So everybody's graph is going to look different. But we will all have the same conditions being held. All right? Okay, we've got those. Let me do this one. F of 1 is 2. That means that at 1, right, my function's value is 2. That means I'm going to come up here and I'm actually going to fill that hole in with a solid dot. So that's this condition right here, isn't it? That has defined our function at 1. Emmanuel, how about this one? We'll say fifth condition here.
So as x approaches 4 from the right?
From the, so it's a minus, right?
Yes.
So think about this. Negatives are over here, positives are over here. So if negatives are over here, we're going to be approaching from the left, okay? So you said as we approach 4 from the left, our function is headed to where?
Infinity.
Infinity. Which means that when I draw this from the left, my function's going to need to do what? What do you mean by keep going? Towards infinity. But that's as I'm getting closer to 4, right? So we're going to actually look at this as almost like a vertical asymptote. And our function is going to do this. I'll just do this. And I'll put a little dotted line here to kind of illustrate. As we approach 4 from the left, our function is taking off towards positive infinity. Do you all follow that? No questions? Sure? How about Juan? Where's Juan? You've got the next one. So kind of in words, tell me what I'm doing here. Okay, the function's approaching 0. What am I approaching on the x-axis? 4 from which side? From the right. Okay, so here's 4, right? I'm approaching from this side, and the function's value is headed where? 0, right? So I can come in like from here down to 0. I can come in from here to 0. It doesn't matter. Now when I get there, I'm going to leave it as an open circle because this does not tell me what's happening at 4, does it? Doesn't tell me what's happening at 4. It's telling me what's happening to the right of 4. All right, last condition. Do we have enough chairs? Are we missing a chair? I know it's kind of tight in here. There's one seat here if anyone wants to sit right here. Otherwise, we have enough chairs and table space. We're a little cramped. Should I ask them to bring another table in next time, or can you handle this? You would prefer another table? Yeah, okay. All right. All right, so who was up? Franklin. Where's Franklin? Yeah, there you go, Franklin. Last condition here. What is this telling you?
Saying that the value actually at 4 is undefined.
Is undefined, which means we definitely did not want to fill that in, right? We actually need to leave this open, and we don't want to put anything at 4.
So the asymptote is not there.
There is an asymptote, but only from one side, which is weird because we haven't really had something like this, have we? We've always had asymptote, and it's always been like from the sides either been this, or it's been this, or they both do that, or both do that. We never had one where it's just from one side it does something, the other side it goes in. If I took this condition out, we could have defined that to be here. We could have. So this is it. This is the function. Now it doesn't really look like a function because it's a bunch of little pieces, right? So what I'm going to do now is I'm going to start connecting things together. And now this is where you have your own kind of artistic freedom here. So I'm going to make my function do this. Put a little arrow. I just decided that's what I wanted the left-hand side to do. Does that change any of the conditions? No. Okay, now here it had to come in here, and then here it was defined, then here it had to come in. And then this is really kind of the next point where I can try and put these together, right? So I'm just going to, I don't know, do something like that. There we go. And then this one's going to be a little rough here, but I'm going to try it. There we go. And then this one, I think I'm just going to put an arrow here. There we go. So now the function is nice and, all the little pieces connect. It is a true function, passes the vertical line test, satisfies all the conditions. Yes?
How do you know if it's over a closed circle view?
I will tell you. Hold on. Another question?
I was just going to say, how did you decide which one to connect that to? Did you connect it to...
Which one? This one?
Yeah. Did you connect it to that one?
To this dot? I don't know. Could I have? Could I have connected this one to this one? Why not? Because what am I supposed to be doing as I approach one from the left?
-1.
I'm supposed to approach here, right? So as I come in here, if I actually connect these, then your limit as you approach 1 from the left is no longer -1, right? It's actually 2, and then you're going to fail the vertical line test anyway because you're going to have points up here and down here. So that the fact that we have to approach -1 from the left forces me to somehow get there from that piece. Now, the question about the open circle, for this one, how did I know it was open? In the first condition, as we approach -2, our function had to be headed towards 3, right? But what happens there at -2 has nothing to do with this information. Remember I said there was like the calculus and then versus the algebra. The calculus, we're covering up what's happening here and just looking at from the left and right. The algebra covers this up and you're talking about what happens here. Part 2 is what tells us where to put that point. Does that help clarify that? Any other questions? Yes?
Is there a certain order in which we should do the steps?
No? You could have done these in any order. I mean, you might have to erase and, because you might, maybe you overextend a line too far and it gets too, what if I had done this? What if I had done I said, okay, I'm going to come out this way and then here, what if I said I went like this? Then you might have trouble connecting these two. You can't do this, right? Why can't I do that? It would fail the vertical line test, right? So you might have to erase to make things connect a lot smoother. There's a few problems like this on your homework. So see how that goes. Anything else I need to clarify there? Remember, everyone's picture is going to look a little different depending on how they decide to make certain things go. But we should all be able to look at the picture and say that these things are true. All right, we're moving on. 1.4. Calculating limits. All right, so far, in theory, okay, we have looked at graphs of functions and we have said, all right, looking at the graph, can you tell me what the limit is? What's it approaching from the left? What's it approaching from the right? But you've been looking at the picture to get that information, right? Now, what we want to do is try and figure out if we can determine what a function is doing as we approach a value without a graph, just by looking at the function itself, the algebraic function. So this may seem like it's going to be harder, and I think it will be a little harder because it's going to require some algebra. All right? So before we actually do this, we need to establish what are called the limit laws. And these are the things that you're allowed to do with limits. And there's a big list of them, and I don't want us to get bogged down on them. I'll kind of refer back to them as I use them, but I will quickly summarize what they're saying. If you're ever taking a limit, as x approaches a, of two functions that are being added together, you are allowed to break it up into two limits. That means if you've got a function with two pieces being added, you can do the limit of each piece separately. Okay, so do the limit on this one, and then take those answers and add them. So you're allowed to split them up. The limit of a sum, the limit of a sum is equal to the sum of the two limits. That's what that's saying. And then the same thing goes with subtraction. So if you're ever taking the limit of two things being subtracted, you can take the limit of each one. Again, you'll see this in action once I do it, all right? This third one is pretty interesting. It says that if you're taking a limit of a function that's being multiplied by a number, that you can essentially ignore the number out front and just take the limit of the function and then multiply it by the number. Again, you'll see it in action. I'll show you an example of these. Property number 4 is a very nice property. You'll come to appreciate it later. It says that if you're trying to take the limit of two functions being multiplied, you can just take the limit of each function separately and then multiply the two answers together. Does it seem very natural that this would work this way? That you're allowed to, like, if it's added, you can split them up. If it's subtracted, you can split them up. If they're multiplied, you can just split them up and do them separately and then multiply the answer. Does that seem pretty natural to you? It's good that it works out this way. It's going to make our lives a lot easier than it could be. If you have division of two functions, you can take the limit of the top and bottom separately. So you can look at them as like separate little universes, do the top and bottom, figure out what the limits are, and then proceed. If you're taking the limit of a function that's being raised to a power, you can actually ignore the power, take the limit of the function, okay, so the limit of what's down here first, then get an answer, and then raise it to the power. So it's almost like the limit can go inside the exponent. It's kind of hard to show you these laws without actually doing examples, all right? But this one's interesting. The limit as x approaches a of a constant is equal to the constant. Okay, let me try and illustrate this one. What is the limit as x approaches 2 of 4? That should be 4. And the reason why is because if I tell you, hey, look at this expression, 4. What happens if I change x here to 2? Well, there is no x there, right? So nothing happens to it. It just stays 4. If there's no x in this expression, then saying what happens as x goes to something should have no impact on the expression. So that's what this is saying. What is property 8 saying? The limit as x approaches, let's go to 2 again. As x approaches 2 of x is equal to 2. That's what that property is saying.
No, that's not a function. It's just
If it's just x, right, by itself, and I say, hey, look, I mean, this is really what this is telling you. It's saying, hey, look, everyone, what happens to x if I let x go to 2? Where does it go? 2. That's trivial, isn't it? It's like, I'm asking you what x goes to when x goes to 2. Well, then x goes to 2. Yes?
What is number 6 again?
I'm going to have to show you an example of that.
Okay.
Yeah, I could do it. Let me do 6. If we have like limit, let's go x approaches 2 of x plus 4 to the third power. Right? Do you see that you have a function? This is a function of x, right? Raised to the third power. What that law says is that I can actually I can ignore the power and take the limit of this. What would happen as x goes to 2 here? What would this expression get close or approach? 6, right? And then I can just cube that answer.
Okay.
6 cubed. That's what that rule is saying. It seems almost like that's what you would have done anyway, but the laws tell us we can do them, right? I mean, we can't ever assume that that would have been true. All right, rule 9, as x goes to a, x to the n turns into a to the n. So imagine I change this right here to x cubed. Limit x approaches 2 of x cubed. That should turn into what then? 2 cubed. Does this almost seem like too obvious, that it's almost a little confusing because it's too obvious what's happening, or is it just like really look weird to you? We're gonna have to do more examples. Don't freak out. It's not worth freaking out about yet. I'll let you know when to freak out. All right, the next one says that if you're doing limit as x approaches a of the root of x, it's just root of a. So something like this. Limit, let's go x approaches 3 of square root of x. What's that going to be approaching? Square root of 3. All right, and this last one, let's just skip this for now. Couple of other things before we begin. We haven't started yet. We're just getting the limit laws and some other things out of the way. This direct substitution property. So if somebody were to give you a function, all right? Here's a function, f of x equals root x over x minus 4. Can anybody just look at that right now? Well, never mind. I was going to ask you for the domain, but it's right here. Why is that domain x greater than 0 and x not equal to 4?
You cannot have negative.
You can't have a negative under the root, right? So your x has to be bigger than or equal to 0 to start. Do you all agree with that? And then here, x can't be 4 because you'd had division by 0, wouldn't you? This right here is called the implied domain. So when somebody just gives you a function like this, it is understood that it has a domain. That domain is called the implied domain. It's implied. By writing the function down, I am implying that there is a domain. I don't have to list it out for you, but you need to be aware of the fact that there is a domain for this. All right? The next little thing is the part that's important. Direct substitution property. If the function we're looking at in this class is a polynomial function, you've studied polynomial functions in college algebra, right? A rational function, you studied those in college algebra, right? Rational function. A trigonometric function, you studied those in pre-cal, right? An exponential function, you studied those in college algebra or pre-cal. Logarithmic function, man, this is like almost the whole slew of functions we've studied, right? If we are looking at any of those functions, then as long as a is in the implied domain of the function we're looking at, then the limit as x approaches a of f of x equals f of a. What? Okay, let me explain. Limit x approaches 3 of x cubed minus 4x squared minus 1 over sine squared x. If I want to know what the limit is as x approaches 3 of this function, then you have to ask yourself a couple of questions. Do you recognize this thing as one of these things? Is that a polynomial, rational, trig, exponential? Is that stuff we've seen before? Yes? Then this property says that as long as the number you're headed towards is in the domain of that, then just plug it in. Just plug the number into the function, and that's your answer. So can I plug 3 into this without having a problem? As long as we don't get 0 down here, right? And sine of 3 is not 0. So I would just replace everything with 3. 3 cubed minus 4 times 3 squared minus 1 over sine squared of 3. And we calculate whatever that is, and we would get some number here. Whatever that number is our answer. All right? So the big picture here is this. If we ever take a limit of something and the number we're headed to does not cause any problems, then all we're going to do is basically what we did in college algebra, and that's just plug the number into the function. Right? And what that tells me is that if I graph this thing, which I wouldn't want to graph that, but if I graph it, what it's telling me is that as I approach 3, from which side? Both sides, that I'm headed towards this number. Now I don't know what that number is because I didn't calculate it. Let's just say it's right here. That's that number. I can tell you this much, that from the left and to the right, from the left and the right, we're headed towards that number. And what's happening at 3, I'm going to just kind of, okay? Now this property is super important because I guess the moral of the story with this is if there's not a problem with the domain, then you don't have to do any work other than plugging the number in. If there's not a problem with the domain. So as you might imagine, the problems we're going to look at today are going to have problems with the domain. Because this would not be worth us spending time on, right? This would not make calculus hard if I'm telling you at the end of the day all you got to do is plug the number in, right? What makes it hard is what happens when that number is not in the domain of this, right? So let's get into our first examples. And I hope that as I work through some examples, this will all start to kind of come to light. Speaking of light, I wish I could turn on some more lights. Yes, is that what you said? Yeah, it's too dark. I'm just afraid how it's going to come out on camera. But you know what? Now that I'm going to be just doing examples, my marker will come out fine. Just when I'm projecting what I put up here, the slides and stuff, they don't come out very good because the projector is not a very bright projector. So, all right, here we go. First problem. Find the limit as, I want to kind of just make up my own problems here. So as x approaches 5 of x squared minus 25 over x minus 4. All right, so what we're asking ourselves is this. This is a function right there, right? That's like f of x. And I'm saying to myself, what happens to that function as I approach 5 from both sides? So if I were to graph it, which I'm not going to, but if I were to graph it, as I approach 5 from both sides, what is the function headed towards? So you look at this function, you ask yourself, all right, is this something I've seen in the past? Is this a polynomial, rational function, trig, exponential? It is, right? It's a rational function. So as long as the number we're headed towards can get plugged in without having any domain problems, then our answer is just whatever we get when we plug it in. So can we plug 5 in and not have a problem?
No.
So do we have a problem?
Yes.
So if you plug 5 in here, what do you get? 25 minus 25. So on the top, I'm going to put a little arrow here. This thing is headed towards, the top is headed towards 0, right? And what's the bottom headed towards?
Isn't it undefined?
The bottom. 5 minus 4? 1. What's 0 divided by 1? 0. Right?
Yes.
You can't have 0 on the bottom, but you can have 0 on top. Right? So there's no problem plugging 5 in. There's no domain problem here, is there? So the answer is just whatever we get when we plug in the 5, which in this case would be 0. So if I graph this right now, what I can tell you is this. As you approach 5 from both sides, it's headed towards 0. I'm not quite sure what it's doing, but I know that it's headed towards 0 as I approach 5 on both sides, right? Yes?
Is it safer to always assume an open circle when you're graphing?
Always assume an open circle. The only way to know what's happening at 5 is to do what? Plug 5 in, right? It does, in this case, turn out to be solid. But when we're talking about limits, we're never talking about what's happening at the number. We're always talking about what's happening as we approach. So what would have been a more interesting problem for me to ask you? The limit as x approaches 4. Wouldn't that have been more interesting?
Yes.
Okay, we're not ready for that yet, though. We'll do that in a second. I'm going to just tweak the problem a little bit. We're going to do a new one. What about this one? Limit x approaches, let's go with 3 of x squared minus 9 over x minus 3. All right, so this is a limit. You look at this thing, is this something that falls into the categories of things we've looked at in the past? Yes. So now we check what happens as we plug 3 in. Do we have any domain problems? This time we do. So what I'm going to do now is to the right, just like I did before, I'm putting an arrow, and I'm going to just calculate real quickly what I get. On the top, when I plug in 3, I get what? 0. And over, when I plug in 3 here, I get 0. And from now on, whenever you see me or you put 0 over 0 up, I'm going to refer to this as being bad. Okay, this is a bad situation. We have 0 over 0. And whenever you see 0 over 0 and you see bad, this means it's time to do some algebra. It's algebra time, okay? It's algebra time. All right, we have to somehow, the way that, so what I'm getting at is if we see 0 over 0, the way we attack a problem like this is to try and employ some algebra into the problem. So I hope that you notice that back in the original expression, x squared minus 9 over x minus 3, that numerator is very special. You can cancel out an x minus 3. How? The top is a difference of squares. So we all have to recognize that the top is a difference of squares. How do we recognize that? By passing 14, 14 and getting into this class. Right? That's a difference of squares. So look, I realize that the weaknesses in my calculus students is always in the algebra. So if you're having trouble with this, look, that's not a good thing, but it's not the end of the world. You've got to get it patched up fast, though. All right? Factoring a difference of squares to this. Now, because I have x minus 3 and x minus 3 here, I can cancel these, right? And that's what you were taught in college algebra. But there's something that is lost in college algebra. Well, I make sure my students don't lose this idea, but when you do this, there's a little asterisk here. You know that small print that you never read on the bottom of something you're about to sign, right? This is a little small asterisk that you may not have been aware of in 1414. When you make this cancellation, you are promising me this, that x can never be equal to 3. That's a promise you're making me by canceling these. It is only this right here. We're about to say that this is equal to what? X plus 3. That's what we're about to say. We're about to say that this equals x plus 3, right? But they are not the same thing. They're not the same thing because if I plug 3 into this, what do I get? 0 over 0. And I plug 3 into this, I get 6. So they can't possibly be the same thing, can they? And the reason they're not the same is because by canceling these factors, you are promising me x will never be 3. If x is not 3, then these are the same. So if you plug 4 into this, you're going to get the same thing you get as you plug 4 into that. You plug 10 into this, you'll get the same thing as you get if you plug 10 into this. These are only equivalent if x is not 3. Are you okay with that? We're making ourselves that promise. Now, we're going to come over here and we're actually going to rewrite this limit. And we are going to break out the algebra now. We're going to do the difference of squares, and we are going to go ahead and cancel these, right? And now on the next line, I'm going to write, notice I'm still going to write the limit. X approaches 3, and now I have x plus 3 here, right? That's all that was left?
Yes.
But I've made a promise to myself that x will never be 3 now, right? You're not allowed to let x be 3. So when we look at this, I'm now going to take the limit, and I'm going to let x what? Approach 3. Does that mean I'm going to let x be 3? No, I'm going to let x approach 3. And that saves us, because we can only cancel that as long as we promise not to let x be 3. The limit is saying, yeah, we're getting close to 3 without actually ever becoming 3. So just imagine you start plugging numbers in here that are getting closer and closer to 3. So let's say like 2.9. If you plug 2.9 in here, what would this become? 5.9? What if you plug 2.99? 5.99. What if you plug 2.9999999? It'd become 5.99999, right? So what is this approaching? 6, right? Right? It's approaching 6. Is it ever getting there? No. But that's the whole idea behind the limit. It's approaching 6 without getting there. Now, it's confusing because I'm telling you, you can do this as long as you promise me x can't be 3, right? But then you're almost like plugging 3 in, aren't you? But it's the idea that as x gets closer to 3, this piece gets closer to 6. We're not saying it ever becomes 6. So now, here's what I can tell you. If I graph this, if I were to graph this right here as a function, then as I get close to 3 here, from the left and from the right, where's my function headed? To 6. Right? It's headed towards 6. And I mean, this is kind of the big deal here. We have actually found a way to get around 0 over 0 here. Haven't we? I mean, we know at 3 the function's undefined. But we know that the closer you get to 3, the closer the function gets to 6. It just required a little bit of algebra. And if you don't believe this, then you can go to your favorite graphing software. I use a thing called Desmos. I've been using a thing called Desmos. And you can just type in the function. It was x squared over minus 9 over x minus 3, right? And if I look at this graph, see, that's so dark. Can barely see it. If I go to this graph and I look at the x value of 3, my function, if I come up here, is what? Well, it looks like it's 6, doesn't it? Yes. That's because the computer doesn't know how to handle a hole. See, there's a limitation on a computer. The computer should actually have a hole there for us, shouldn't it? Because it is undefined. At 3, it's undefined. But as I come in from the left, where's it headed? 6. As I come in from the right, where's it headed? 6. You see that? So when you graph things, be careful on your calculator. It doesn't show you holes. But there is technically a hole there.
Is that 2?
Pardon?
Is that 2?
Is that what?
Was it F2?
Did I do 2? Did I just do it right here? I thought I did here.
Oh, 3.
3 and 6, right? Okay. All right. Should we do another example? Of course. How about this one? Limit x approaches 4 of x squared minus 16 over, x squared minus 2x minus 8. So the first thing I'm going to do, and the first thing you should always do with all limits that you're ever faced with, is to just try and see what would happen if you just replace all your x's with 4. In this case, with 4, right? So let's just see where this would head. Where would the top go? 0. Now the bottom might require a little more calculation, but this is going to be 16. We're going to take away 2 times 4 is 8, and we're going to take away 8 again. So we're going to get 0 again on the bottom, aren't we? So this is 0 over 0. This is bad. And this means algebra, right? Now, how did we handle the last problem? What kind of algebra did we need to do for the last problem? Some factoring, right? So this problem factors similarly. The numerator is a difference of squares. So it becomes x plus 4 times x minus 4. What about the denominator? It's a trinomial, right? So does that factor? How does that factor? X plus 2, x minus 4. So again, this is one of those things where if the factoring part of this is trouble, this is where we need to get the defibrillator on you quick. Okay, can I cancel anything? Yes, the x minus 4s, right? So long as I make a little promise that x will never be 4, but that's okay because I'm taking a limit. I'm letting x approach 4, so that's okay. So now I write limit x approaches 4 of x plus 4 over x plus 2. And this is kind of where those limit laws start to come into place. Like, since I have a quotient, right, I can do the limit on the top and bottom separately. So I just let x go to 4 on, x is going to approach 4 on the top, x is going to approach 4 on the bottom. Where is that headed to? If that's going towards 4, then this is headed towards what? 8. If that's headed towards 4, this is headed towards 6, right? So this is headed towards 4/3. Are we saying that at 4, this is 4/3? If we're saying, are we saying that if we plug 4 into this, we get 4/3? No. We're saying that as you approach 4 from the left and from the right, the function is approaching 4/3. So if I were to graph this again, we would have a hole, and the computer would not show us the hole, but we would definitely be approaching 4/3 from both sides. Are we all right so far? All we've needed so far to do these problems is some factoring, right? Difference of squares, factoring a trinomial. We've been okay with that? This one, limit x approaches 2. X minus 2 over x squared minus 2x. Yeah. Back to the sticks. Gabriella? Gabby? Yes. Where's my numerator headed here? Zero. Top's headed to 0. How about the bottom?
That can't equal 0, else it's going to be undefined.
What can't?
The bottom.
The bottom? Is that what you're saying? Yeah. If the bottom, is the bottom headed towards 0 though? So 2 squared, 4 minus 2 times 2 is 4. So 4 minus 4. So we get 0 again. This is bad, right? And Gabriella, anytime we see bad, we think what? Algebra, right? All right. So Heidi, where's Heidi? Heidi. I know I met some of y'all already in my office, and I'm sorry, I still names I'm not good with, but I could tell you a little bit about Heidi, but I'm not going to. So I'll know about you, I just don't necessarily won't know your name. Okay. So what was I going to ask you, Heidi? Oh, what sort of algebra? Do you see any algebra that you could do here, Heidi?
You can pull out an X.
Out of the denominator?
Yeah.
Everyone see you can just factor an x out of the bottom? Just pull that x. So this factoring is even less than we did before. It's just a GCF, right? Greatest common factor. And then those x minus 2's will cancel. So long as we promise that x is never 2, but it's a limit, so we're approaching 2. So this is a legal move. What's still up on top? We still have a 1, right? Notice how when I'm writing this, I keep writing limit. Do you see how I keep on writing limit? And it isn't until the very last step that I stop writing the limit. I stop writing the limit at the step that I actually let x go to 2. That's when I won't write it anymore. So here at this step, I'm now going to let x go to 2, and this thing's going to head towards where? 1/2. And we're done. Does that seem okay to you so far? Okay, how about this? Limit x approaches 1, x cubed minus 1 over x squared, hold on, I have to think through these, plus 4x minus 5. Yeah. Luis. Right, it's Luis, not Louis?
Yes.
Luis. Are you ready? Have you had time to write it down? Okay. What's it headed towards, Luis?
0.
0 on top?
Yep.
What about the bottom?
0.
It is 0 on the bottom also? Everyone confer with that? Is there anyone who has not given me a stick? Because I'm taking attendance off these, so is anyone? No? Is this your first day? No? It is your first day. Well, then you're supposed to come up here and do a speech, right? We all did 5-minute speeches first day? It was 5. It was 10, but we can't waste time. We can't waste time. No, I'm kidding. We didn't do any speeches. But you need to write your name down on this so I can call on you, or else you're going to be counted absent. Yeah. Yeah. If you're smart, you'll write Heidi's name again, something like that. All right. Where were we? Luis? 0 of 0, which means bad, which means you don't have to write bad in algebra, but if it makes you happy, you can do it. I don't mind writing it. It's bad. Okay, so that means some algebra. And
I have a question.
yes,
What if it's not bad?
what if it's not bad?
Yeah,
Then your answer is whatever that number is.
Okay,
Okay, so let's say this came out to be like 2 over 3.
so,
Your answer would then be 2/3.
okay.
And that'd be it. And I'm glad you brought that up because I've been known on a test to make the first problem look really bad. And you're like, all right, I'm going to show off all my algebra skills now. And you start doing all this factoring and stuff, and you realize that you could have just plugged it in. It was 2/3 or something, and you never had to do any algebra. So just be careful because we never want to overlook that first step of just seeing what's happening. And if it's not bad, just write it down. We're done. Okay? All right. What kind of algebra can we do here? Factor the bottom. Okay.
What how much experience can you put at the top? A difference of cubes?
It is a difference of cubes. Yes. But let's do the bottom first because you mentioned the bottom. So how does that factor?
X minus 1, x plus 5.
X minus 1, x plus 5. Now look, maybe you've noticed this in the last few problems, that if you get 0 over 0, that means that there's going to be a common factor. There's going to be something that has to cancel, right? And that common factor should always be whatever would be required to make x equals 1 be 0, right? So x minus 1 is a factor. If you go back and look at all the limits we had before that had 0 over 0, if you look at the number we went to, we had the factor x minus that in here on the top and bottom. So when you're looking at that right there, you can actually say to yourself, I know x minus 1 is a factor of that. Like I already know that. So you could write x minus 1 down and then go try and figure out what the other part is. That's just a little shortcut. All right, now on the top, difference of cubes. This is a difference of cubes. So there is a formula for this, and I don't necessarily expect that you would have it memorized, but it is on your formula sheets. And I don't recall how it is on your formula sheets, but I'll just give you the formula the way, here, just like this. If you have two things, a difference of two cubes, it will be x minus y times x squared plus xy plus y squared. That's the formula for difference of cubes. There's also a formula for the sum of cubes, just while we're doing this, which is very similar to this. The only difference between the two formulas is that's a minus, that's a plus, that's a plus, that's a minus. Both formulas have pluses here. But these are on your formula sheets. So when we see up there x cubed minus 1, right? That 1 is really 1 cubed, isn't it? 1 is 1 cubed. That's what this is. And so this should factor how? According to the formula, it's this one right here. Right, so we have x cubed minus 1 cubed. So it should be x minus 1, x squared, plus x times 1, which would be x, and then plus y for us is 1. So 1 squared is 1. So the numerator factors like this. And, you know, I said there should be a common factor, right? And there it is. Yeah, the x minus 1. And now the x minus 1s can cancel. And now go ahead and at this point, I guess we could rewrite the limit. So this is equal to the limit as x approaches 1 of x squared plus x plus 1 all over x plus 5. And that is equal to, now let's let x go to 1. And we can get rid of the limit as long as we let x go to 1. And what do we get? 3 on top, 6 on the bottom. So 1/2 when we reduce the fraction. Any questions? So in the problems we've done, we've had to do difference of squares. We've now had to do difference of cubes. We've done greatest common factor, right? That's the type of factoring we've done. Is there any other things that we might need to be able to do? Oh, yes. Oh, yes. We're just getting warmed up here. How about this one? Let's let x approach 6. Let's go square root of x minus square root of 6 over x minus 6. Trey, you happen to be the top one here. I don't know how that happened. All right, Trey. So what is happening here as you let x go to 6? What are you going to get here? 0 on the top. Everyone good with that? Root 6 minus root 6 is 0. Okay, the bottom? 0. Okay, so this is bad. We're going to do some algebra. So the reason I'm here is to try and help you these first, do these problems and kind of be like, yeah, you see how I did that? Like, now you know. Okay, now you know. So this one, I wouldn't expect anyone who hasn't done this before to see this necessarily. So sometimes you just have to be shown kind of the tricks of the trade, and then we go from there. So does anyone have an idea?
You square the top.
What was that?
Square the top.
How do you mean square the top?
Just square root of x by squared, and then negative 6, or square root of 6 by squared as well. That gives one of the squares, and you have x minus 6, and then you cancel that.
Okay, so you're thinking if I square the top, then it will turn into the bottom.
Yeah.
Okay. Let me challenge that idea. If I asked you to square this, right? That would be me squaring the top, wouldn't it? If I square the top, I would actually not be allowed to square each one. To square this, you would have to FOIL it out. You would have to actually do this and then do this, right? And that would be different than had you squared each one. That's if you squared the top. But on top of that, if you square the top, it's no longer the same problem. Because if I give you a function, you just go square the numerator, you no longer have the same thing, right? You've done something to it, you've changed it. So you might think, okay, well, I'll square the top and the bottom. You can't do that either, right? You cannot square the top and the bottom of something and it still be what it was before. Yes?
And rewrite that as square root x minus 6, and then square that?
Square root of x.
Minus.
Oh, combine them. So can you? You're saying this. Is that equal to this? I guess that's a question you have to ask yourself. Are those the same? Are they? How could you convince yourself that it's not? Just plug a number in. Okay, let's plug in 9 here. What would you get if you plug 9 in right here? Root 3. So if I let x be 9, then right there I get root 3 equals, now if I do 9 here, what would I get? 3 minus root 6. Are those the same thing? Pretty sure these aren't the same, right? Anytime you have a question, whether or not something's equal, best thing to do is plug a number in and see if it's still equal. If it is equal, test about 10 more, okay? Because you might have got lucky that first time, all right? So algebraically, I can't square the top and bottom. Can't do them individually or separately, can't do that. Can't combine those together. So what can we do? Yeah? Factor the bottom. So remember that first day of class I said, like we have algebra and then algebra on steroids? And like, can you realize that this is a difference of squares? Right, I said that first day. So that will work. I'm going to do a slightly different approach though, because it's something that we'll do later and you should see it now. I'm going to multiply this by 1. But the 1 is going to be something very special. It's going to be the conjugate. I'm going to multiply the top and bottom by the conjugate of the numerator. Now, factoring the bottom, difference of squares, would work and you get the same answer. Okay? But this, coming in with the conjugate on top and bottom, is a pretty standard procedure. So I want us to all see it and be able to do it. Okay, any questions first of all on what the conjugate is? It's just this expression, change the sign. If it's minus, I change it to plus. Now, why do we bring in the conjugate? Because it works. All right, so let's see what would happen here. I'm going to multiply top and bottom. Okay, here we go. This becomes the limit as x approaches 6. Just get used to writing the limit over and over and over. All right, it's just part of what you're going to have to do. Now let's go ahead and multiply out the numerator. What's that? X. Okay, what about the next term? This and this would give me plus root 6 times root x, right? I'm going to write this one down since this is the first one I'm doing. This would be root x times root 6. Now, you can put those together, but let's just leave it there. Is that all right?